Hi guys, welcome back to another video. In this video, we're going to be talking about graphs and topological sorting. So essentially, this is going to be like a homework assignment that I did in my data structures and algorithms course. And it's one of the assignments that I had a lot of fun with. It was definitely like interesting to learn about graphs and how to sort them and how to make them. And so hopefully I have this video out by today or tomorrow. Today's Tuesday, or today's Monday actually. And then I'm also going to record a video about my Spotify API project that I want to get back into. I've worked on it a little bit off camera, but I want to get back to like the same style of videos that I was doing before, where basically I'm just coding and like figuring stuff out as I go, and then you guys can see like what I do like not in real time, but like I'll show you what I do like consecutively, and then if I have to backtrack and like delete and start over, like you guys can see that like basically like the coding process of everything that I do. But today's video is just going to be me explaining graphs and topological sorting. I'm going to be going through all of the functions inside this program, and hopefully you guys can learn a little bit more about graphs and topological sorting. We're going to implement our graph using an adjacency list, and then I'm going to explain everything like what that means in a little bit. So what we can use graphs for is transportation problems like databases, connectivity, and computer networks. So specifically for this topological sorting problem, we're going to need a directed and acyclical graph, which is essentially a DAG, which means like each edge has like a direction that it's pointing to, and there's no cycles within the graph. And so we use an adjacency list because our graph is sparse, and if we were to use another sort of representation, we would do an adjacency matrix, and that's more useful if the graph is dense. So essentially for topological sorting, it's going to be sorting by who has the most edges, and then we'll calculate it using the in degree. There was like pseudocode in my textbook that helped out a lot, but I'm going to try to explain it here based on my code. Or actually, let me pull up the textbook, because it'll be easier to just explain it through pseudocode, and then I'll just show you like what I did with my graphs. So first off, we're gonna start with looking here. So this is just basic code that we were given, and then actually let's start off here with explaining like the graph data structure. So the graph has a vector of vertices and a vector of ints, which is its adjacency list, and this is its list of vertices or vertices. So each vertex has a label, it has an in degree and a top num. Both of these are going to help us in the calculation of the topological sort. And then there's a struct here, which is a cycle found exception. So if a cycle is found, then this exception is thrown, and then the program just ends. We do that. So for each line, we make a vertex with the first number, and then we push it back to the node list, which is the vector filled with vertices. And then we create an adjacency list for that particular vertex. And then we just loop through here. So while the edge does not equal -1, you just push back another vertex inside the adjacency list within that line. And then you do that for each line in the input file. So here we just have display graph, and then display graph is, let me just run it here. So display graph is essentially just this piece of output right here. It displays the vertices with its edges that correspond. Alright, so now we're getting into the topological sort. So first off, before topological sort, we have to compute the integrity. For each vertex, it computes how many vertices are pointing into it. So for example, you see here, the final integrity for 1 is 0, because based on the file we were giving, there's no edges here that point to 1. So integrity for 1 would be 0. Yeah, so essentially here it says we're going to get a vertex's adjacency list, and then we're going to iterate through it, and whichever value of it is at, like this is the iterator, we're going to add 1 to that vertex's integrity. So for example, as we go through 1's adjacency list, we add 1 to 2's integrity, we add 1 to 4's integrity value, and then we add 1 to 5's integrity value, and we do the same thing throughout. That's how we calculate integrity. And then this is just to print out the integrity. So once we have integrity, now we can get into topological sorting. So as I said before, topological sorting is kind of based on the integrity of each variable, of each vertex. Okay. So now we go into the topological sorting. In topological sorting, as you can see, we use a queue and we use a counter int that's going to help us. So first off, we're going to on-queue each vertex that has an integrity of 0. So those are the first ones that are going to be put into the queue. So as we know, a queue is, let me just write out a picture. Please ignore my bad handwriting. But as we know, a queue is first in, first out. So here we have, this is the first vertex that gets put into the queue. It's the one that have integrity 0. So then, while the queue is not empty, we're going to say vertex B is going to be the queue, the vertex at the front. Then we're going to pop it. Okay, so give me a second to understand what top num does. It's been a while. So I'll go back to this. So then after that, after we add 1, we add the counter plus 1. We set that equal to top num to the vertex V. Okay, so vertex V is still pointing to the value we had at the front, but then we pop it. So then that value gets deleted off the queue, but we still have it in V. So then V's top num is equal to counter plus 1. So if we were looking at the first one, counter would now be, or top num will be equal to 1. Oh yes, okay, so top num is essentially the order that we're going to use to print out the topological sorting. Okay, so here we see that is right here. So now we're going to go back here. Have this down here. So maybe I can explain it a little bit better using this. So here we have integrity. So this one is going to be the first one that goes into the queue and gets popped out. So this counter is going to be equal to 1. So then we go to 2. Then we go to, okay, so then we go to, this is essentially saying go to 1's adjacency list. So basically adjacency list at the 0 index. So we're going to iterate through that. So at each of its values 2, 4, and 5, we're going to subtract 1 from the integrity. And if that is equal to 0, for example, 2, it's equal to 0. Then we're going to on-queue. And then 4 is going to be equal to 2. We're not going to on-queue yet. And then 5 is equal to 2. So 2 minus 1 equals 1. We're not going to on-queue that. So then we can get out of this. And then here we see that the node list at 0, so the vertex 1, its top num is going to get assigned this counter right here. It's going to get assigned 1. Yes, so this is going to be 1, and that's why yes. Okay, so this node list.v.label minus 1 still corresponds to vertex 1. So we're going to assign vertex 1 counter plus plus, which is 1. And that's going to help us in the printing. So then we're going to do another loop so I can continue this logic. So then we're going to go to while Q is not empty. Q is not empty because we have 2 on the Q. So we're going to pop that. So we're actually, first we're going to set, that vertex 2 equal to V. So then we're going to pop the Q and pop the front. Then we're going to set 2's top num equal to counter plus plus. And remember, the last one counter was equal to 1. So this one is going to be equal to 2. 2's top num is going to be equal to 2. Okay? And then we're going to do the same thing. We're going to get 2's adjacency list. Then we're going to iterate through that. Then, then we're going to say if the vertex 3's in degree, we're going to subtract 1. Then if that equals 0, we're going to on Q. So here we see that the in degree of 3 is 1. So minus 1 is going to be 0. So we're going to Q that. So now 3 is at the top of the Q. So then we check 4. 4 is equal to 2, not 3 right now. So then minus 1 is going to be equal to 1. We're not going to put it onto the Q. And then 7 is still not going to be put onto the Q. So then we can get out of the for loop. So now we're going to assign 2's top num is going to be assigned to V top num. So it's going to be assigned 2. And then it checks to see if the graph is in a cycle, which is not. So it's going to go back into the while loop. So then it's going to keep doing this until it goes through all the vertices, and then we're going to have our topological sorting like this. So as I explained, we popped 1 first, and that was going to be the first topological sorting. Then 2 was on-queued, then it was popped. So then 2 becomes the next value, and then it goes on and on. And then I forgot to mention this, but essentially counter is supposed to equal the node list dot size at the very end. So if it doesn't, then that means there was a cycle found. And so if there's a cycle found, it means we can't really compute the topological sorting because it just keeps going around and it's not a directed acyclical graph. Okay, so that was just a rough introduction to topological sorting and graphs. I hope that made sense. It definitely helped me out a lot trying to explain it to you guys. So I hope you guys enjoyed, and if you guys have any suggestions on videos that you'd like to see, I have other projects that I am working on. So if you guys want to see those, they are related to data structures and algorithms. If you guys want to see those, please let me know in the comments. I'll leave timestamps so you guys don't have to watch the whole thing. And stay tuned for my video on my Spotify API. I really want to finish that soon and upload it to my GitHub. Speaking of which, all this code is available on my GitHub, and I'll make sure to leave a link below so you guys can check it out. Thank you guys for watching, and see you guys in the next one.